Hello students, today I'm back with another lesson. This is all about irrational numbers. So in the last session I discussed what the number system is all about. Yeah, I told you that it has been classified into two main systems. Your one part has your rational numbers, where you have all the numbers that you have been studying so far. And irrational number forms a completely different family. So today precisely we'll understand their properties and how exactly can we draw them on a number line, which is a very new concept. You must not have done this before. Even if you have done in school, I want you to revise it once again so that you don't forget, because questions often come directly based on marking these irrational numbers on a number line. Okay? So, irrational numbers, they form the complete opposite of rational numbers. Your rational numbers are always in the form of a fraction. Any number I can represent in the form of a fraction, those are rationals. Yeah, all the numbers that you have been studying, natural numbers, whole numbers, fractions, decimals, negative, everything you consider, they were all rational numbers. So if irrational numbers form the complete opposite, we look at the definition of rationals first, and the complement of that, or just the opposite of rational, becomes your irrational. So as I told you, rational numbers are always in the form of p by q, where these p and q are individually integers, where there is only one restriction, that this q, the denominator, is never equal to 0. Okay? Now, you must have seen fractions. Some fractions give you a perfect number, like for example 16 upon 4. Yeah? You get a perfect answer for this. 16 out of 4 is just 4. If I give you 20 out of 5, it again gives me 4. Yeah? Or even think about those kind of fractions where you do not get a proper answer and you leave it as fractions itself, like 1/3. If you were to simplify this, you would get 0.3333, and that keeps on going. Yet it is still a rational number because it justifies the statement, the definition of rational numbers. So what could be the opposite of these numbers? So after studying rational numbers, you have to ask yourself, have we left any sort of numbers behind, or have we considered the entire system? Well, there are certain numbers which cannot be represented as a fraction, where both values are your integers. Now, consider scenarios like finding the square root of 2, or you have a square, and in this square, if this side is 1 unit and obviously the sides are equal in a square, if you were to find the diagonal, this diagonal would never be a number which is perfectly decimal, or something I can write it as a fraction. Okay? Why? Because by using Pythagoras theorem, you would figure out that this value, this diagonal, which is the opposite of 90 degrees, it happens to be the longest side. This is obtained by taking the square of the other two sides and you add them up, and then you find the square root of this value. So when you find the square root of this, clearly square root of 2, there is no perfect number that multiplies with itself to give you that 2. So such numbers cannot be represented as fractions. So what is the simplest definition you can give for irrational numbers? Would be any number which cannot be represented as a fraction, where I have both numerator and denominator as integers. Okay, cannot be expressed as p by q, where p upon q are integers. If I have to tell my experience about studying for irrational numbers for the first time, I used to wonder one thing. What about root 2? Why do we even call it irrational? I can write this as a fraction. Yeah? I can definitely write this as a fraction. So what's the problem? I used to think that. Okay. Now, that used to be my question. But the thing is, I guess I overlooked the definition of rational numbers. Rational numbers, as in I must have both numerator and denominator as integers, and clearly root 2 is not an integer. Okay, so I don't want you to have that same confusion, honestly. Okay. All right. So cannot be expressed as fraction p by q, where p and q are integers. That is the main definition of irrational numbers. Now, if a number is either rational or irrational, they form the entire family together. The entire family, we call it is now real numbers. Okay, that is the entire family of numbers that you'll be studying till class 10. There you will assume for now that there is no other numbers than real numbers. In reality, yes, of course, you have these real numbers, sure. But when you come to class 11, you'll study about entirely different family. So for now, you will just stick to real numbers. Every real number is something I can represent on a number line. Okay, I can actually represent any value on a number line. So where exactly do these irrational numbers belong to, or where exactly can I locate these irrational numbers? In order to do that, we follow a particular method of locating irrational numbers on a number line. And there is a trick, there is a logical trick doing this method, and I'm going to show you how exactly we do that. It's interesting, very interesting. So, before getting into that construction part, the other way we express irrational numbers would be these kind of numbers. If you use your calculator to find square root 2, you will see a number that's never terminating, a kind of decimal that's never terminating. So we call it non-terminating, non-repeating. Unlike the rational numbers, where you see that digits are repeating like this, it is not possible for irrational numbers to repeat after the decimal, or they do not repeat in a pattern. Okay, of course the digits will come once or the other sometime. Okay, we just have countable number of digits, so these digits do appear again, but not following a pattern. Okay, so non-terminating, non-repeating decimals, that is the other name for irrational numbers. All right, so this is it. This is the main definition of irrational numbers, and now I'm going to show you how exactly we locate them, and I'm going to take you to a different site. All right, so to locate these irrational numbers on a number line, you can think of the simplest irrational number first, square root 2. Okay, think about square root 2. How exactly do you locate that number on a number line? To begin with, I will start by drawing a number line, definitely. So here I'm taking a number line. Okay, so on this number line, let me mark 1 point. This is my 0 or 0 units. Okay, now I'm taking this value. not this. This one. So this is my 1 unit. I'm saying this is 1 unit. I want to make it big enough so that you can say this is 1 unit, then clearly this has to be 2 units, right? And this will be 3 units. Okay? Now what I'm going to do, this is the exact procedure for locating numbers on a number line. If you'll understand this once, you'll not forget it. What you'll do is you'll need a compass first of all. Take your compass and mark it at 0, like this. I want to take it at 0 actually, just a second. Oh my God. Okay, just a second. It's not exactly at 0, just a second. I need to keep it exactly at 0, okay? My marking here is not letting me keep my compass exactly at the center. Just a moment. Am I allowed to keep it here? It's not taking me. Okay. All right. So let this be my 0, okay, for the timing, because my compass is definitely not allowing me to take it at that point. So I'm just saying this is 0 units, this is 1 unit, and this is 2 units, okay? And I also don't have the option to clear off, or else everything goes off at once. So this is my compass is now kept at 0 units, okay? What I'm going to do is I'm going to take the length 1 unit, okay? I need to take the length exactly 1 unit. So once I've taken, this is my 1 unit length, mark it like this. Now what you're going to do is, from this 1 unit length, you want to draw 90 degrees, okay? You want to draw, because you're trying to draw a square actually. So you want to see where that 90 degree is. So I clearly see my 90 degree has to be here. All right. This is my 90 degrees line. So now what I'm going to do is I'll take my compass. I've already measured 1 unit here. I'm going to take my compass to that point where I was before. From here, I just want to mark that 1 unit on that perpendicular line. Okay. Once I'm done with that, why did I do it? Because I know 1 unit base and 1 unit height makes the hypotenuse exactly equal to square root 2, right? Using Pythagoras theorem, if I'll work out, then 1 square plus 1 square is 2, and then taking the square root of that gives me the length of the hypotenuse. So if I'll do that, this is exactly square root 2. This length that I've drawn is exactly square root 2. So now the best part is you got the length of the square root 2. What you'll do, take your compass back again and now measure this length with your compass, the square root 2. If you have measured this, this is the length of square root 2. So now the radius of your compass is exactly square root 2. Lock your compass and get that arc right here on the number line. Congratulations, this is where your square root 2 should be. If you use your calculator, you will get the answer 1.414 and it goes on, okay? So it clearly shows me it's less than 1.5, yeah? And this is exactly where square root 2 has to be placed. Interesting, isn't it? Because you really cannot use 1.41 exactly, or because that is not the exact value. So this is the exact accurate method of constructing or locating the square root 2 on a number line. Now think about square root 3. How do you think you can obtain square root 3? To obtain square root 3, if you want the length to be square root 3, when will you get the length square root 3? Think about one side is square root 2 for a right triangle. Okay, if this is square root 2 and this is 1 unit, then think about the hypotenuse here. To find the hypotenuse, what will I do is simply square the other two sides. So square root 2 will be squared and 1 will be squared. That gives me the length of this hypotenuse, whatever you call it, OA. So the square of OA has to be equal to the square of the other two sides, sum of the squares of the other two sides. So square root 2 when squared gives me exactly 2 and 1 squared is 1. So OA alone has to be the square root of 2 plus 1. 2 plus 1 is 3, so square root 3. So to locate square root 3, you need the side length square root 2. And luckily, we have already constructed it, or we have got where that square root 2 is. So you can do one thing. What you can do is, now because you have got the length square root 2, right? You measure 1 unit exactly again. This is 1 unit. So we want our side lengths to be square root 2 and 1. So this is already square root 2, right? From here, if I'll mark 1 unit somewhere here. Now to mark 1 unit, again you have to draw that 90-degree line, because you want only the two lines are perpendicular, then we follow the Pythagoras theorem. So therefore, at this point, at this particular point, you will take your protractor and let's measure 90 degrees exactly from that point. This is how I'll measure 90 degrees. Well, this is the 90-degree line. Okay. Now, because I have drawn a perpendicular line and I have actually measured 1 unit by my compass, I am going to measure 1 unit on this perpendicular length. Hi, I hope you are understanding what I am teaching you. Yes, Vimore 7K LRM, I don't know. Okay, so yes, I hope you're getting what I'm teaching here. And yes, let's get back to the same process. Okay, I'll come back to you, don't worry. So now, because I've already measured 1 unit length on this perpendicular line, what do we do? What do we do is, I will just make sure. Okay, I can read your message well. I'm not able to chat like on the chat itself. Yes, I do teach class 8 math. Don't worry about that. For now, I'm currently doing 9, so yeah, I will definitely do class 8. Okay. So coming back to this perpendicular line, I have drawn the square root 2. Now I have this perpendicular line where I've measured 1 unit. So once I've measured this 1 unit, what I'm going to do is I'll take from the center, from the origin, I'll measure out this. Now that length, you clearly see it's more than the previous length we got. Okay. So this is now equal to square root 3. Why? Because I showed you by Pythagoras theorem. If I'll take one of the side as root 2 and the other as 1, then my hypotenuse obtained will be square root 3. So therefore, this length now becomes the radius of your compass. change the radius and keep it exactly square root 3 like this. Lock your compass and, well, you clearly see square root 3 is a little further from square root 2. Use your calculator to verify how much will that be. It's 1.732 goes on, okay. So I clearly see that this value I got is more than the previous one. The previous one was root 2 and now this is root 3. Alright, so this is how exactly we locate irrational numbers on a number line, okay. Now, if you were to continue this process, okay, now from here if you had to draw a 90-degree line again and think about square root 3 plus square root 3, if I'll whole square it and add it to 1 unit again, I'll get the square root of 4. Now, square root of 4 is exactly 2 units, yeah. If you were to continue this the way I'm doing, then you would get a spiral actually. Okay, you will get these irrational numbers continuously. Note that square root 4 is not an irrational number. Not all square root numbers are irrational. Yeah, because if you can think about 4, then 4 is a square of a perfect whole number 2. So therefore, if a square root number can be represented without the roots as a perfect whole number, then it has to be rational. Okay. So all square root numbers, or you can clearly remember one thing, the square root of non-perfect square numbers, they are always irrational. Think about 6, square root of 6 is definitely irrational. Square root 7, square root 8, now square root 9 will definitely be rational again. So this is how you locate any irrational number on a number line, okay. Now sometimes the question might tell you to locate root 5 on a number line. There is nothing I can do actually with, regarding the views. I'm not worried about views as of now. For now, I think I'm mainly here to, tell all my students like you that we are just starting, so I guess we will have more views in the coming classes. Let's hope for the best. That is what I can do. And I'll continue to teach. It does not matter for now because obviously I love teaching. That is the main reason I'm teaching. So let's hope for the best, You never know what might happen next. So yeah. Thinking about locating square root 5 on a number line. You can do it without entirely having to do all of this. Think about square root 5. When do you think the hypotenuse length will be square root 5 now? Now 5 being very close to 4, I can think about square root 4 being one of the side and 1 being the other side. Why? Because think about this. Square root 4 is how much? 2, correct? So let's say if my triangle has one side 2 units like this and the other side is 1 unit. The hypotenuse should be how much? Let's figure it out. This is 1 unit, this is 2 units, okay? So what's the hypotenuse here? I'll take the square of 1, I'll take the square of 2, and whatever value I add them or whatever I get them upon adding, I'll have to take the square root. That is how you find the hypotenuse. So 1 square is 1, 2 square is 4, so square root of 1 plus 4, which is equal to 5. So that is how I'm going to obtain square root 5 on a number line, by taking one of the side as 2 units and one of the side as 1 unit. Let's do that. Okay. Oh. See, I actually showed you how to work out square root 5, okay. To do that, what will you do is you'll take one side as 2 units, one side as 1 unit, alright. And taking their squares, adding them up, take the square root, that is how my hypotenuse will be square root 5. Alright, I'm going to show you again. This is one of the, commonly they ask for square root 2, 3 or 5, not usually for more than that, okay. So you can expect one of these to come in your exam, honestly. You again begin with a number line. So you have to mark one of the lines as 0, one of them at 1 unit, 2 units. I mean, just take your lengths, take your units as equivalent length, okay? You don't have to have that as 1 centimeter of your scale. It can be 2-3 centimeters considered. You can consider 2 centimeters as 1 unit. So this is equivalent to 2 units here, right? And let me draw 3 units again. So let's say this is 0, 1, 2, 3. I showed you to draw or to locate square root 5 on a number line. You have to take 2 units on one side. So I'm going to take from 0 to 2 here as my first side. Now at 2, I have to start with the 90 degrees, or I have to draw that 90-degree line. I have to draw that height. This is my 90-degree line, yeah. And now take your compass again. It's measuring 2 units. We want only 1 unit to be our height, okay. One side is 2 units, the other side has to be 1 unit. Taking their squares, adding them up and taking the square root makes root 5. So once I've located that 1 unit, from the origin or from the starting point, I will measure out this length. Once I've measured this out, I'm going to take my compass again, make this as my radius, because now my compass tells me that this length I am marking on with my compass is exactly root 5. So lock your compass and start measuring this. The length that you got on the number line is exactly root 5 now. You know root 5 will be more than 2 because square root of 4 is 2. So square root of 5 has to be more than 2 logically. So you got that. Isn't it simple? It actually makes a lot of sense, and this is how you represent irrational numbers on a number line, okay? So this is the concept of locating irrational numbers on a number line. There are more topics coming up that talks about solving for rational numbers itself, or operating with these non-terminating repeating decimals. At the same time, we also learn how to operate these irrational numbers, yeah? So if you are confident with this part, then you should move to the next part, which is all about understanding the properties, okay? So my next lesson will be all about mainly the properties of rational numbers, or in that particular session I'll talk about, I'll talk about these non-terminating repeating decimals, okay? These fractions which cannot be, so conversion of these non-repeating decimals to fraction. That is one of the most important thing you have in class 9, okay? And you will be studying this for the first time in class 9. So I want to do that with you, followed by properties of irrational numbers. I'll do one topic at a time so that each topic you study, you you understand clearly, and you really don't have to look at this topic again. That is what I'm trying for. And if you have to if I have to tell you what kind of questions come from this part, mainly, yes, locating irrational numbers. They usually ask for locating these irrational numbers. Apart from that, they'll ask you whether some number is irrational or not, okay? So if I'll ask you, for example, Is root 2 plus 3 rational or irrational? This is the kind of question they ask from this section, which is kind of easy to answer, because if you're adding an irrational value, this is irrational. If you're adding irrational to rational, then the result is always irrational. It's like if you are adding odd plus even, then the answer is always odd. Likewise, if you have irrational plus rational, the answer is always irrational. So if you're adding or subtracting an irrational number, if you have a rational number A, you do plus or minus a root number B such that it cannot be written as a perfect whole number. Yeah, B has to be a non-square number. So it is always irrational. Okay. Now remember one thing, it is not that only your square root numbers can be irrational. Think about cube root numbers, or let's say if I'll ask you the cube of 2, the cube root of 2, then well, that is also something I cannot represent as a perfect answer or perfect number or even a perfect fraction. So that also has to be an irrational number. Okay. Now they'll ask you some tricky questions. Questions will be like, give an example of two irrational numbers that adds up to give you rational. Now that is interesting, isn't it? Think of two numbers such that they are irrational, but they give you the sum or the difference rational. How is that possible? It's only possible when you take the equal and opposite irrationals, like plus root 2 and minus root 2. Yeah? Upon taking their sum, what happens is definitely I get 0, which is rational. Now the same thing applies when I said a plus minus root b, that is always irrational for sure. But if you have two irrational numbers, okay, root a plus root b or minus, because I'm saying the values here are different, a and b, I'm using two different variables, I'm clearly saying that they are two different numbers. And provided these square root numbers are irrational themselves, then their sum or difference is also irrational. Because there is no way I can get the answer some real number, or some rational value. Okay, rational is possible only when I take the opposites. Remember that. Now, is it possible that I multiply two irrational numbers and get a rational? Well, it is. So let's say, for example, if I'll take square root 2 and then times it by the reciprocal of that. Now note that 1 by root 2 is also irrational because one of the number here is irrational. So their product is rational. Interesting, isn't it? Because it is possible that I take two irrationals and operate them to get a rational number. That is still possible. Okay. Similarly, think about taking two irrational numbers like square root 2 times square root 3. Then obviously the answer has to be square root 6. Why? Because it comes from the properties of exponents. For those of you who don't know that square roots can be written as powers, think about square roots just the opposite of squares. Okay, so if I have to represent this in power form, this is one of the things that we have coming up in the following sections. The square root always represents a power of half. Why? Because square root, as the word suggests, root, it represents the reciprocal of square, which is 1 by 2. Okay, so that is how I'll represent, and square root 3 is how much? 3 to the power 1 by 2. So you must have studied this in exponents, that when you have two numbers multiplying together such that their powers are same, how do you deal with them? You can write them together, you can multiply them together and raise them to the same power. If you'll do that, it becomes 2 times 3, 6 to the power of half. Now, which can be represented as root 6. Okay, so this is irrational now. So this is the reason why I'm saying it is possible that you multiply two irrationals and the result can be both rational or irrational. Okay, so they might ask you to set many examples. Don't forget about these reciprocal numbers which are both irrational but their result, their product is rational. Similarly, don't forget about multiplying two rational numbers to give you, if you have to multiply two rational numbers to give you, not irrational. If you multiply square root 2 with square root 2, then what happens? You get 2. So these are both irrationals. So product of irrationals can be both rational or irrational depending on what two numbers you are taking. Okay? This is really interesting because you just have to explore numbers. Okay? You have to think about examples that could give you both kind of result. Alright? And I am hoping that you're understanding and things are making sense to you. All right, I can see a lot of things coming up here, and well, I hope I'm able to clarify your concepts based on rationals and irrational. Yeah, I hope you will never have the problem to identify rationals with irrationals. And similar to this, there are many things, many properties of irrational numbers that you have to understand and explore. Alright, but section 1.2 is mostly about locating irrational numbers on a number line and identifying irrational numbers and distinguishing from the rationals. So this is the main part. This is what you have. And apart from this, we have this new part coming up that is all about terminating and non-terminating decimal. That is a fun thing, and this topic will very soon come to an end. I would also like to do a lot of questions based on your book. Not only from your book, I'm going to use some reference book along with the main book, so that whatever you have to study in this topic, I'll try my best to cover up as much as I can. Okay, so with this, I think we have covered a lot of things. Okay, and I hope you have understood the concept of locating irrationals, the properties, and to cite some examples of operating with irrational numbers to produce rational or irrational results. Yeah. So if there is anything you need help in from this topic, please feel free to tell me in the comments, and I will definitely see you in the coming lesson for the upcoming section. That is it for today, and I'll see you in the next coming session.